There is a distance so vast, so utterly beyond the reach of anything we have ever built or imagined building, that the word impossible feels almost too gentle. We are talking about crossing the Milky Way, our own galaxy, the place we call home in the cosmos. And when you sit with the actual numbers, when you let the mathematics speak without flinching, you arrive at a conclusion that is simultaneously humbling and astonishing. No species, no matter how advanced, no matter how patient, no matter how brilliantly engineered, can cross the full breadth of our galaxy in any meaningful sense. The universe has built barriers into its very structure, barriers made not of walls or obstacles, but of the deepest laws of physics themselves. Let us begin with the scale, because without feeling that scale in your bones, none of what follows will carry its full weight. The Milky Way stretches roughly 100,000 light years from one edge to the other. A light year is the distance light travels in an entire year, moving at approximately 300,000 kilometers every single second. That is not 300,000 kilometers per hour, that is per second. In the time it takes you to blink, light has traveled nearly the full distance between Earth and the Moon. Now hold that speed in mind and ask yourself, how long does it take light to cross our galaxy at that extraordinary velocity? The answer is 100,000 years. Light itself, the fastest thing in the physical universe, requires 100,000 years to make that crossing. Now, we are not made of light, we are made of matter. And matter, according to the deep principles of special relativity, can never reach the speed of light. This is not a technological limitation waiting to be overcome. It is not the kind of problem that more funding or better engineering will eventually solve. It is written into the mathematical fabric of space-time itself, as fundamental as anything in all of science. As an object with mass accelerates toward the speed of light, something remarkable and deeply counterintuitive happens. The energy required to push it further does not just increase. It increases without bound. You could pour every joule of energy in the observable universe into accelerating a single spacecraft, and it would still fall short of light speed. The closer you get, the more energy you need, and the required energy curves upward toward infinity. Infinity is not a very large number. Infinity means there is no amount of energy, no matter how staggering, that closes the gap. So the speed of light is a ceiling that matter cannot touch. But physicists are imaginative people, and over the decades we have asked, well, what if we got very close? What if a spacecraft could somehow reach, say, 99% of the speed of light, or 99.9%? Would that not be enough to cross the galaxy in a reasonable time? And here is where special relativity introduces one of its most elegant and deeply strange gifts, the phenomenon of time dilation. When an object moves at speeds approaching light, time as experienced on that object actually slows down relative to time experienced by a stationary observer. The faster you go, the more dramatically your onboard clock falls behind clocks at rest. So imagine a crew accelerating their ship to a significant fraction of light speed and making that 100,000 light-year crossing. From the perspective of the Milky Way, from the perspective of any civilization left behind, over 100,000 years would pass. Every person they knew would be long gone. Every city, every culture, every record of their existence would likely have crumbled into dust. Stars might have shifted in the sky. The landscape of the galaxy itself would have changed. They would return, if they returned at all, to a galaxy 100,000 years older than the one they left. But there is a deeper problem that time dilation alone cannot rescue us from, and that is the problem of energy. Getting a spacecraft to even a modest fraction of light speed requires energy on a scale that staggers the imagination. The energy required scales with what physicists call the Lorentz factor, a quantity that grows slowly at first and then explodes toward infinity as you approach light speed. To reach 10% of light speed, you need to accelerate a ship to 30,000 kilometers per second. For a spacecraft massing even a few thousand kilograms, the energy involved rivals the entire output of the sun over many years. To reach 50% of light speed, you need vastly more. To reach 99%, the numbers become so extreme that no physical energy source we know of could come close to providing them. The most efficient fuel imaginable, according to physics, would be matter-antimatter annihilation. When a particle of matter meets its antimatter counterpart, they annihilate each other completely and release energy with 100% efficiency, far beyond any chemical or nuclear process. And yet, even with perfect matter-antimatter fuel, crossing the galaxy would require a mass of fuel so enormous that it would dwarf the mass of any reasonable spacecraft by many, many orders of magnitude. The rocket equation, first derived for simple chemical rockets, grows more punishing the faster you want to go. You need fuel to carry the fuel. You need more fuel to carry that fuel. The math spirals into absurdity long before you reach the speeds required to make a galactic crossing viable. Some thinkers have proposed alternative approaches, ways of cheating the rocket equation rather than fighting it directly. The concept of a Bussard ramjet, for example, imagines scooping up hydrogen from interstellar space and using it as fuel on the fly, eliminating the need to carry propellant from the start. It is an elegant idea on paper, but interstellar space is almost unimaginably empty. The density of hydrogen atoms between the stars is so thin, perhaps 1 atom per cubic centimeter on average, that the engineering required to collect enough fuel would produce more drag than thrust. The ramjet idea, when examined closely, runs into physical walls that imagination alone cannot break through. Then there are the proposals involving laser sails, enormous reflective surfaces pushed by powerful laser beams fired from a home star system. Breakthrough Starshot, a real and serious scientific initiative, explores this idea for sending tiny probes to our nearest stellar neighbor, Alpha Centauri, about 4 light-years away. And even for that comparatively modest journey, the engineering challenges are immense. Scaling such a technology to carry anything resembling a crew and to aim it not at the nearest star but all the way across a 100,000 light-year galaxy crosses from engineering challenge into physical impossibility at multiple levels simultaneously. There is also the question of what space itself is like at these velocities. At high fractions of light speed, interstellar dust and gas, which seem negligible at ordinary speeds, become lethal. A single hydrogen atom encountered at 99% of light speed carries the energy of a high-speed bullet. Over 100,000 light-year journey through even the most rarefied regions of the galaxy, the cumulative bombardment from such particles would destroy any physical structure we could conceive of building. The cosmos that looks so empty from our slow vantage point becomes a radiation environment of extraordinary violence at the speeds required for even a roughly plausible galactic crossing. We should also sit with what quantum mechanics and thermodynamics tell us about the long-term fate of complex systems. Any spacecraft, any crew, any life support infrastructure is a physical system subject to entropy, the universal tendency of order to degrade over time. Even if we imagined a ship that could somehow maintain its structural integrity across the kind of timescales involved in a galactic crossing, the second law of thermodynamics demands that disorder accumulates. Components fail, information degrades. Living biological systems require constant repair and maintenance. Across timescales of tens of thousands of years, the challenge of maintaining any complex ordered system against the relentless pressure of entropy is not merely technological. It is a confrontation with one of the most fundamental principles in all of physics. And even the idea of generational ships, vessels so vast that entire civilizations live and die aboard them over the course of the journey, does not escape the physics. The energy requirements to sustain a living ecosystem across a 100,000-year voyage, to maintain breathable air, drinkable water, viable food production, structural integrity, shielding from radiation, all of this for 100 millennia is staggering in a way that defies practical consideration. The sun has been burning for about 4.5 billion years. 100,000 years is 2% of that. It is an unimaginable span of time on any human scale, yet a tiny fraction of astronomical time. Now, some of the most ambitious thinking in theoretical physics has explored the possibility of shortcuts through the fabric of space-time itself. Wormholes, sometimes called Einstein-Rosen bridges, emerge as mathematical solutions from the equations of general relativity. They describe hypothetical tunnels connecting two distant regions of spacetime, potentially allowing passage between points that are enormously far apart in ordinary three-dimensional space. The mathematics is real. Einstein's equations do permit these structures, but physics gives and physics takes away. For a wormhole to remain open and traversable, it would require exotic matter, a form of matter with negative energy density. Ordinary matter, every kind of matter we have ever detected or created, has positive energy. Exotic matter with the required properties has never been observed. There is serious theoretical debate about whether such matter can exist at all within the constraints of quantum field theory. And even setting aside the question of exotic matter, stabilizing a wormhole against collapse, threading it with a passage wide enough and stable enough for a spacecraft, and navigating through it without being shredded by gravitational tidal forces represents a set of engineering demands so far beyond anything physically achievable that it belongs firmly in the category of speculation rather than possibility. Warp drives, another concept rooted in real mathematics, specifically the Alcubierre metric, propose contracting space in front of a ship and expanding it behind, effectively moving space itself rather than moving through it. The mathematics does not violate special relativity in principle because the ship is not moving through space faster than light. The space around it is moving, but the energy requirements calculated for even a modest warp bubble are extraordinary. Early estimates suggested you would need an energy equivalent to the entire mass of Jupiter converted to pure energy just to move a small region of space. More recent refinements have reduced these estimates, but they still point to energy scales orders of magnitude beyond any conceivable physical energy source, and the theoretical problems multiply. Creating negative energy on the scale required, maintaining the geometry of the warp bubble, stabilizing the structure against quantum effects, all of these represent barriers that even the most generous theoretical treatment has not successfully dismantled. What all of this tells us when we gather the threads together is something profound about the structure of the universe itself. The cosmos did not simply end up being very large by accident. The laws of physics, the speed of light, the geometry of space-time, the behavior of energy and matter at extreme velocities all conspire to make the universe vast in a way that has real consequences for any physical entity within it. The galaxy is not merely far. It is far in a way that the laws of physics enforce. Space is not just a neutral backdrop across which beings travel. It is a physical entity with properties that create genuine, insurmountable barriers. There is something almost architectural about this. The universe seems to have been constructed with distances that are immune to clever shortcuts, with speed limits that are written into the deepest level of physical law, with energy requirements that no power source can match, and with time scales that outlast any structure made of matter. Whether one views this as a kind of cosmic isolation or as a reflection of the extraordinary richness of what exists within our own small corner of the galaxy depends perhaps on temperament. But the physics does not bend to temperament. Our own solar neighborhood within a few hundred light years remains the only domain within which sustained physical travel might be conceivable across long but not infinite timescales. The nearest stars are 4, 10, 20 light years away. Missions spanning decades or a few centuries remain within the outer limits of physical and biological possibility, even if still enormously challenging. But the galaxy, the full 100,000 light-year breadth of our home island of stars, lies on the other side of a threshold that the laws of physics draw firmly and without exception. The universe is telling us something with this arrangement, something quiet but unmistakable. The laws that govern reality are not merely inconvenient obstacles. They define what is physically meaningful, what can persist, what can travel, what can reach. And in that definition, they give the cosmos its particular character, vast, ancient, largely silent from any single vantage point, and populated by islands of complexity that are, at the deepest physical level, unreachable from one another across the full width of the galactic stage.